Okay, all right. So thanks, everyone. I'm going to talk about um, future, about like immutable systems. I think there are things we do in Yocto project that kind of dovetails into that. We'll discuss some of that, and we'll also talk about um, heterogeneous compute. So essentially, I think as you can see, more and more non-CPU compute units are becoming prevalent. Uh, it's a time for us to see how we can fit into that world, which is rapidly changing. Feel free to ask questions in between discussions. We can continue on that one. And I'll also present some of the parts where, the project is doing some stuff which paves way into it. And maybe, there is some food for thought after this. All right. So let's talk about immutable systems to begin with. And what's an immutable system? It's primarily that doesn't change. Essentially, you can boot into it, and you really don't allow a lot of the properties that you'll see on desktops today, and we'll talk about those. So here are some of the immutable distros, that are spawning out of desktop distributions today, and I'm talking about the binary distributions. If you look at, there's the Fedora Atomic project, and they have Silverblue and Kineot. Silverblue is, the traditional Fedora spin, and Kineot uses KDE. But fundamentally, they are based off of same technology, which is RPM OS3. And I think, some folks here might have deployed OS3 in their distributions using Open Embedded as well. RPM OS3 essentially is that, where RPM is sort of front end to OS3. Vanilla OS, which was based on Ubuntu, I think, but is based on Debian now. And it uses containers for doing their application management. Bland OS is, again, it's based on Arch. And NixOS is, another interesting distribution. What it uses a declarative language to define your system, essentially very similar to what WIPA does, in terms of recipes and config metadata. It's a seemingly same space, same way of doing things. MicroOS is a open source, I think Tumbleweed based, and Less OS, I think, is Debian based again. What you see is there is this trend of building these distributions out of the binary distributions out there, and they are being made to fit into different use cases. And so why are immutable systems needed? Give me a second. So they're secure because you're using a read-only base system. So essentially, chance of accidental modifications is hard, even if there is some aspects of malware coming in, you may not be able to modify your base systems. However, if you can root the device, then all bets are off. Still, it raises the bar, so that's why it is way more secure. And any changes that you do locally, they get lost on reboot. And it's reliable, because sometimes when you install in place some of things on your desktops, they bring in different dependencies. Perhaps, they start interacting with some of your existing packages in some ways, and change your system without your notice. In this case, this won't happen. And your systems is only updated after you reboot it. So some of downsides you'll see, if you're taking a desktop view, it's difficult to install additional software. The traditional package management won't work out of the box. You have to know flatpaks, snaps, or app images, containers, some of the ways of doing the installs. And layering, you would use RPM OS3, or you have to know containers. And there are container tools right now where you can install a full distribution and just for one app, for example, on a base system which is immutable. So I think there are these kind of tooling that is available, but it can be a bit of learning experience there. So therefore, not straightforward if you're, knowing a way of updating and maintaining your existing systems. Updates is a big one. So there is no in-place updates that happens. Essentially, those, you basically are building another image. It could be you base it off your existing rootfs snapshot and then apply, any delta changes. And create another image to boot for. And sometimes you can use, file system which supports snapshots, for example, ZFS, ButterFS, and you can use that way as well as a starting point. And if something goes wrong, it's easy to roll back because you'll have a policy to keep your previous images around. And there are different ways people do it. Some of them have, dual, like symmetrical banks, so they boot from one and prepare the another one after reboot, switch to that. And then you can easily switch back if something goes wrong in there. So it's easy for you to roll back your system to a previous state. And there are also asymmetrical updates. So far, I think, some of things will be familiar to some of us here who build embedded Linux systems. These are similar techniques, how they are being used. My point to discuss them here is that they are also being considered now in general, distributions. So what are some of the common principles? System upgrades won't happen on live systems. I think, some of them, they do allow some of it, but generally, you do the update offline onto another system by preparing another image or another partition, and then you reboot into it. So essentially, they won't happen on when your system is booted and working. Kind of makes it atomic from that point of view. And as I discussed earlier, rolling back is easier. You can just reboot to a previous snapshot or previous image that you were booting off before the upgrade. And in some cases, you can have multiple snapshots, so you can go back to any of those snapshots. So considering this and what we do in Yocto, we already have provisions that someone can use for immutability. There is a distro feature called read-only rootfs, so you can deploy that. And some aspects of reproducible builds help in there as well, given that your recipe data remains consistent. You can get a reproducible build. And there is a support for some of the update mechanisms, OS3 container support, is meta virtualization. We talked about it yesterday. And then there are OTA solutions from vendor, Swapdate, and others. And they do provide you A/B update mechanisms, or asymmetrical update mechanisms, or different ways to lay out your system so immutability can be achieved. In some cases, you prepare a separate partition for your applications, and your base OS is a separate partition, and so on and so forth. So there are different ways. They are very rich in laying out your OTA solutions that are there. They can lay out the system in different ways. And there is some efforts that we have done to do things that are happening at runtime during build time, for example, static UID, creation, and we have mechanisms to execute some of the things that general distributions do on first boot. You can do that as a post install, and that post installs are actually executed when you're building an image. So that gives you an opportunity to build an image that is not modified at runtime. However, if you consider real systems, there always will be, data partition that will keep for data persistent, maybe some config data that you need to keep persistent. So essentially, immutability is relative in that regard, because if you have a read-write partition, things can go wrong. So essentially you apply an update, maybe you're storing a database there, and the format changes, you upgrade it, now you're downgrading it, and now you need to downgrade the database as well, and boom, it doesn't understand, or it can't be downgraded, the database format, for example. So there are things of that nature you need to take care, but essentially, I think as far as I see, there are all ingredients of creating an immutable system that are already in there. And we basically can build a very good immutable systems currently, given all the primitives we have in the project. You'd see that there are, generally these are some things that are also getting more familiar in the desktop user space, specifically if you build specific systems that needs to behave in certain way and manage, the immutability becomes quite useful for creating consistent systems. So I'll go over heterogeneous compute, and essentially I think this is something that is interesting. What is heterogeneous compute in that I'll cover today? It's basically you have multiple compute units. Essentially, you have traditionally a CPU which does most of the processing, and in this case you have more different kind of compute units that are on the system. These days, GPUs, CPUs, NPUs, FPGAs, and all of them can be used in different capacity to run the workloads, general purpose workloads, that is. So that's where the heterogeneous compute is interesting, or becoming more interesting. So far, we've seen that it was centered around CPUs. So, you have the ABIs, even in software, they were primarily developed around CPUs. Programming languages, they are very aware of, your CPU architectures and, different things that you do, specifically optimizations and other pieces, you take into consideration a lot of your architectures, for example. And software stacks, they are also targeted at presuming CPUs underneath, essentially. So it's more or less that the whole stack is built as if it will run on a homogeneous computer. And so the heterogeneous computes could look something like this, where you have a multi-core CPU, and then they have some sort of interconnect, that connects to the memory, and memory is exposed basically coherently to your different compute units, whether it's a DSP or it's GPU or CPU. And then, data is shared either coherently or in some cases maybe non-coherent. But as you can see, there are hardware provisions that are available to you. And in this case, what happens is now, there is a potential for you to share a lot of data between these different heterogeneous computes, but then you need to have a mechanism to do that. And Why it is moving towards that, end of Moore's law, I believe that, essentially now it is going parallel, different kind of compute units, basically, right kind of hardware for right kind of software sort of thing. And you want to extract, performance, but not give up on energy efficiency, so essentially you want to offload some of, specific tasks perhaps that are more optimal for specific compute units. And in some cases, there is heterogeneous execution. So, some portions in parallel can be executing on CPU and other, compute units in parallel, which can give you a more performant system. So here I've considered, some of the common cases, but, you can have different kind of specific purpose compute units, but you'll find these in today on systems. So, multi-core CPUs. In some cases, you'll find symmetrical, some cases asymmetrical cores like, big, little, and GPUs. Essentially, when in embedded space, you have any SBC today, you'll have a GPU on that, and they are pretty good from doing what they were traditionally supposed to do. You can do a lot of other kind of compute on that, like specifically vector processing and things of that nature. DSPs are already there. They were you can do specific tasks with parallel hardware threads. So essentially, you can do some compute, which may be in same kind of performance that you would get on CPU, but at a very low energy consumption, for example. And NPUs, these are in this similar fashion where some of the aspects of NPUs you want to kind of offload, and FPGAs get into the same kind of category. So now, given all this, what should a SDK look like, right? So essentially, there are a few things I've listed here. Kernel is actually a piece of software that you put together, that you will offload or send to one of the compute units, right? So it can be a OpenCL kind of a workload, or it could be a function or function pointer or some sort of like Lambda that you push down to CPU, or DSP. So, some portion of piece you can generate using DSP specific code and push it down to DSP. Now the challenge is that how do you manage this distribution? And there are like which kind of CPU you want to execute. If you're on big, little, you need some sort of awareness, energy awareness, or performance awareness. And how would you manage the shared memory? I mentioned in previously, their memory is heterogeneous. What kind of interfaces do you want to have in shared memory? And parallel execution tasks, how are they managed together? They will run asynchronously in parallel. How do you synchronize the data? And those are kind of, there are a combination of software, hardware primitives that are required there. And a couple of them, I think OpenACC is one, and then OpenMP is another one. And you can see there's a GCC and LLVM, support that is available. I think OpenACC, I'm not that sure whether LLVM supports it, but I did see MLIR, dialect for OpenACC, so I'm assuming there is some sort of support. But OpenMP is well supported, and you'll see the new OpenMP GOMP. We are producing libgomp and other runtime today, which is one part of as I was mentioning previously, how do you manage the runtime? So OpenMP essentially is one of those, and it's supported in GCC and LLVM. And interestingly, MLIR, which is a multi-level IR, which is currently implemented in LLVM, but it is pretty interesting because it can generate, you know, heterogeneous code. Basically, it can, the way it is organized into dialects, you can define easily a new dialect, maybe a domain-specific dialect. So, as this more specific compute units come along, it'll become easier to retarget code for them, and that's where MLIR will be instrumental. And I've listed a few links here. If you look at the users link in there, you'll be surprised how many different kind of compilers, domain-specific compilers, are already using MLIR. And all of these are being used in some sort of machine learning and some sort of heterogeneous compute tasks. And I think that MLIR is not very, very old, but it's kind of being used quite a bit. So I think if you look at this, we have all these SDKs in some form, right? But there is no a distributed or a standard way to distribute it or create a system for this. So right now it works in some ways, but I think there is probably a space for creating a distribution where you can retarget maybe some of this, like what we do with multi-libs, or where we can target specific RTOSes, bare metal and Linux, and we can build a full system. This takes a little bit more granular, where you can create a binary that is basically consisting of all these kernels. That can be then offloaded to these runtimes like OpenMP, and they can execute. So I think there is a good opportunity for the project to be able to build and distribute such SDKs, and even build a full system, that where you can take a general purpose application and probably accelerate that by using the heterogeneous compute underneath, perhaps. So I think some of the initial things that comes to my mind is support MLIR and LLVM as part of the core, and maybe start there, where you can put together maybe a one dialect to begin with, and then see that can be made more generic. So that's what I had. So if there are questions, go ahead. Feel free to ask.
So we have a couple minutes for questions. Somebody asked if CUDA support is problematic.
So CUDA is, yeah, it is or it is not. So essentially, you got like OpenCL and CUDA. Essentially, these are runtimes. There are more out there that are coming. OpenACC, I mentioned one of them, but yeah. So I think there are also aspects where people are building, systems which can distribute to or generate code for, say, CUDA or OpenCL or others underneath. I think there will be this will be there, like if CUDA is there, others will come up. I don't think there is going to be a single standard that you will have in terms of runtime for this, but in general, I think right now you do get tool chains, modified compilers and things like that, which you can build CUDA software today. But I think, yeah, in order to become, more, it can be more generic, I think, and that's where I think Yocto could be very, very useful, where you can basically generate for whatever your runtime is underneath.
I know I've heard of some gymnastics so that people can actually build FPGA images with probably very complicated recipes. And Chuck, are you ready to go?